Hello and welcome to another one of TZD videos. Today we're going to be looking at an example of optimization. So we're making a poster and we want 100 square inches of print, and the question is asking, what dimensions would I need to have in order to have 2-inch margins on the sides and 1.5-inch margins on the top and bottom. We want to minimize the area of the poster. Alright, what is step one? Step one is always to draw a diagram. So make your best attempt at doing a rectangle within a rectangle, because that's what print is, right? So here's my print. You will note that I have put the margins on the sides of 2 inches and 1.5 on top and bottom. The print is 100 square inches, and I've labeled that my length and my width. Okay. So now that I have my diagram, I need to ask myself, what do I know and what do I want? Well, I know the area of the print, so that's going to be my constraint, the equation that relates the variables together. And I want the area of the poster, or the page, or whatever you want to call it. So let's see. The area of the print, if I assign this width and length, is going to be length times width. And I want to choose the print because that's what my 100 is going to equal. Right? So what you do is you set your area of print equal to your constraint. You will be able to solve for one of the variables in your main equation here to eliminate it here in a little bit. So what will happen is we will have another equation, the main equation, the area of the poster, and we will have two variables in that equation. And you as a student don't know how to, a Calc 1 student don't know how to come up with the derivative of two variables quite yet. So let's see that in action. The area of the page, the poster, is going to be the lengths and the width plus some measurements. Okay, so for the length up and down, we have 1.5 on top, 1.5 on bottom. So the poster is going to be whatever this length is plus 1.5 plus 1.5. Well, that's going to be the length plus 3. And then the same logic would give us the width, left and right, plus 2, which is 4. To give you this equation. And you see what I mean? There's a L and a W in our equation. You don't know how to derive that yet. So what you do is you set your constraint equal to 100, the print, solve for one of the variables, and then you get L equals 100 over W. Now what you want to do is you want to take your 100 over W and plug it in for the L. That way you can make your area only in terms of W. So you plug in this L right there, and then it's all in terms of W. Well, what I would do, instead of using the product rule to derive this, I would FOIL it out and get a much easier equation to work with, a little algebra. Not to say that that product rule would be difficult, but it's just easier to work with the power rule. Less mistakes. Unless you don't know how to FOIL, then I suggest you go back and review how to FOIL, but you could use a product rule at that point. So now, take the derivative. And when you take the derivative, so there's the derivative. The derivative of a constant is 0. The derivative of 3w is 3. If you bring this up, make it w to the negative 1, bring it down, subtract 1 from the exponent, you get this. So the step after that is to take the derivative and set it equal to 0. So if you do that and solve, what I do is find a common denominator. Don't bring stuff over to the other side. It'll be too tempting to cancel out one of your critical points. So here we would have a common denominator of that, just multiplying by w squared over w squared on this first term. Then if I set the numerator equal to 0 and solve, I get plus or minus 200 over 3. If you remember, you can't have a negative width. W is a width, so you ignore your negative value right there. Okay, you can't have it. So then we get 20 over 3. We can rationalize and do our first derivative test. So when you rationalize to get rid of the radical on the bottom, you multiply top and bottom by the root 3. So in the first derivative test, what you can do to get a local or relative extrema, in this case a minimum, plug in a test point to the left and the right of your critical point into your first derivative. Alright? So this will give you a decreasing. When I plug in a 1, 300 minus 400, or 3 minus 400 is definitely negative. Plug in 100, you get 3 minus some tiny fraction, which is definitely positive. So then when we go decreasing, then increasing, that's a relative minimum. The problem is we only have one dimension, so we got to get the other dimension. So how do we do that? Well, if we're looking for what L equals, wouldn't it make sense to go to the equation that says L equals? So go up there, plug in, simplify, rationalize. There's your other dimension. All right? So at that point, we're not done. We actually have to give the dimensions in sentence form with the units. So it'll say the dimensions that lead to a minimal area of the page are that by that inches. If they wanted the minimal area, all you would need to do is either plug in W there or plug in L and W here. Alright? So draw the diagram, come up with your constraint and main equation, solve your constraint for a variable, plug in, simplify, derive, find your critical points, prove it's a minimum, find the other dimension, and then conclude with a sentence. All right? I hope I've clarified things a little bit by working this example for you, enough to give you courage to try some, because practice is the key to understanding all these